Nature's battleground. Animals fight for their survival. Out of this conflict, an extraordinary weapon has evolved. One that forever changed the rules of engagement between predators and prey. It is one of evolution's greatest achievements. The eye. The animal kingdom encompasses millions of species, and more than 95% of them share a common trait: the power of sight. Eyes are everywhere, but look closer. No two species see the world in quite the same way.
Animals have a tremendous variety of eyes. We see different appearances of eyes, we see different sizes of eyes, we see different configurations of eyes, and this is because animals have different lifestyles.
Among the sharpest eyes in the animal kingdom are those belonging to birds of prey. Searching high in the sky for tiny prey demands remarkable vision. And birds of prey have evolved eyes that are second to none. This eagle spies its prey from more than a mile away. Even while diving at speeds of 200 miles per hour, it tracks its target with deadly precision. The secret to the eagle's success? The anatomy of its eye. In most cases, the larger the animal's eyes, the sharper its vision. And the eyes of the eagle are huge. Eagles are 100 pounds lighter than we are, but their eye weighs the same as ours. Size is just for starters. The back of our eye has 200,000 light-capturing cells per square millimeter. The eagle's has 1 million, providing 5 times the image resolution. Its lens is flatter and placed farther away from the retina than ours. The result? A gaze as sharp as a telescope, magnifying its helpless prey to 3 times what our own eyes can see. What force drives the development of such a remarkable innovation? Evolution. The sparks of evolution are tiny, random genetic changes.
Every once in a while, there's a little mistake made when the DNA is passed on from generation to generation. And those mistakes are called mutations. And sometimes the mistakes cause problems, other times they create new opportunities.
Mutations that boost survival and reproduction are favored by natural selection. Species that can't adapt disappear. 99% of all species have gone extinct over time. The survivors are equipped with mutations that have given rise to uniquely powerful traits. The eagle has evolved one of the most powerful eyes in nature, but it is just one of the many different types of eyes that have evolved over time.
Animal eyes are an excellent example of convergent evolution. All the eyes on different animals across the planet today did not evolve from the same ancestral eye. In fact, eyes have evolved numerous times in different lineages.
Remarkably, evolution has used the same basic genes to build the eyes of creatures as profoundly different as flies, squid, and humans. Research points to an origin for these building blocks of all vision 600 million years ago. The Earth's oceans are calm. There are no monstrous predators to contend with, no creatures armed and ready for combat. Sea life is simple. Animals come in 2 sizes, small and extra small. They're soft, with little protection, and they have one speed, slow. But it is here that one group of creatures took a dramatic step toward vision. These pioneers are long extinct, But one of the oldest living lineages of animals still swimming in today's oceans provide a peek into the past. Jellyfish. Biologists Alex Goodell and Chad Widmer of the Monterey Bay Aquarium are on the hunt for a test subject.
Go get him.
One that can give them insight into the roots of vision.
Oh, yeah, that's a nice looking one right there, yeah.
This is Polyorchis, more commonly known as the bell jelly. The anatomy of this delicate creature is about as simple as animals get. It has no skeleton, no heart, and no brain, just a loose network of nerves. But it has a crucial innovation that its survival depends on. A ring of small dark spots line its base. Light-sensitive organs called eye spots. We can only imagine what these most basic of eyes can see.
Vision for them is very different than for us because we are able to form images quite well and they aren't. So it's kind of more of a blurry world for them than for us.
Scientists don't know why the distant ancestors of modern jellies evolved light-sensing cells when they did. But Goodell can show how they have helped jellyfish survive for 600 million years. She has designed a simple experiment showing how bell jellies use light detection to their advantage.
I'm interested in seeing if different animals that don't form images can see different colors if they respond to different wavelengths of light.
Goodell subjects the jelly to light waves that it would find in its natural environment. First, she hits the jellyfish with a dose of green light. On cue, its body goes limp and drifts to the bottom of the tank.
See, the tentacles are getting longer.
Oh, yeah, yeah. So you can definitely see when they're relaxing. The tentacles extend, they pulse less frequently.
The green light usually makes them appear to relax. They usually will drop down to the bottom and their tentacles will extend and their bell pulse rates will decrease.
Why does green light put the jelly so at ease? It's the wavelength of its home turf, the ocean floor.
They usually spend most of their time on the bottom where they would naturally be getting a lot of green light. They find most of their food on the bottom, so they're used to being in this type of light.
Goodell then switches things up. Purple light fills the tank. Suddenly, the jelly pulses wildly.
When I flip on the purple light, the jellies seem to go into this escape response. Their tentacles shorten up and their bell pulse rate increases.
It's a reaction akin to us fleeing from a fire. To the jelly, purple light means one thing. Injury, or even death, might be imminent. The reason is simple.
Short wavelength light, like purple or ultraviolet, blue lights, it's actually higher energy, and it can be very damaging for organisms that are transparent. So a lot of transparent animals rise up in the water column in the evening and hang out on top at night. And then in the morning, as the sun's coming up, they migrate back down.
Light triggering action. A simple vision system, to be sure. But it's helped jellyfish survive over 500 million years as they find food and evade predators. But the eye's evolution would not stop there. More than 500 million years ago, the calm waters are to be overrun with a new breed of creatures. Eyes are about to get a powerful upgrade and unleash an evolutionary arms race that will forever change life on Earth. The dawn of the Cambrian period, 544 million years ago. The animal kingdom is undergoing a time of transition. Early animals were simple, passive creatures, drifting through the current or anchored to the sea floor. But over the course of 50 million years, a lot is going to change. Life undergoes an explosive transformation. thousands of new species burst into being, including the oceanic ancestors of dinosaurs, elephants, and humans. This is evolution's Big Bang, the Cambrian explosion.
For that time, there was little, if any, animals present on planet Earth. And within about a 20 to 30 million year period, basically all of the major animal groups appear in the fossil record and start diversifying. So it's a time of major evolutionary change.
Scientists like Bruce Lieberman are discovering ancient clues about why the explosion happened.
This really is one of evolution's big unanswered questions. Darwin talks about the Cambrian explosion in The Origin of Species back in 1859, and he was puzzled by how quickly organisms appeared. We'd like to know what were the triggers that caused this real explosion of life.
The creatures that emerged from the Cambrian were larger and more mobile than any of their predecessors. And what's more, they evolved weapons for battle.
An important aspect of the Cambrian explosion is that it is an evolutionary arms race.
For the first time, creatures evolved the natural weapons they still use on today's battlefields: jaws, claws, body armor, and most critical of all,
Eyes appear. They're obvious, they're there, and there's no evidence for complex eyes before this Cambrian explosion.
these eyes are the first type to appear in the fossil record: compound eyes. The invention of a group of arthropods called trilobites.
Arthropods are joint-limbed animals that today include things like crustaceans, insects, spiders, and so on. The compound eye is a type of eye that's possessed by these arthropods.
On closer look, it's clear that these eyes are nothing like our own.
So you can see these two round structures on the head, and when you look at them in detail, you can see small circular bodies in a series of rows. Each row has several of these circles, and when we look at them, you can recognize that these are eyes with many lenses.
Trilobite eyes are one of the earliest results of the animal kingdom's most feverish arms race. Coincidence? Or was the evolution of more powerful eyes the spark that triggered the Cambrian explosion?
Eyesight is part and parcel with predation and things avoiding predators. So if there were not the development of eyes, you might have had some of the sparks of the Cambrian explosion, but I don't think you would have had the full bang.
Just how did the trilobite manufacture an eye of such complexity? They took advantage of the materials at hand. Their eyes are made of rock.
This rock is calcite, and in fact, it's the same rock or mineral that makes up the trilobite eye.
Trilobites secreted this mineral from their skin to form both their rigid shells and equally rigid eyes.
That's what their skeleton was made of. They had to evolve an eye out of this substance. So it means we've got a beautiful record of what their eyes looked like. Without calcite, trilobites would be not only naked, but blind.
These crystal eyes represented a major advance from the simpler light-sensing cells that came before, and likely gave trilobites a supreme survival advantage.
The eyes present before the Cambrian explosion would have been nowhere near as complex as the type of eye that you'd see in a trilobite. The compound eye would have allowed them to better track down prey or find dead carcasses of things to eat.
True visionaries, trilobites diversify and endure for nearly 300 million years before a mass extinction event wipes out the last of their species. But other arthropods survive, and one group takes the compound eye to new heights: insects.
If we look at the most abundant animal life form on land, it's the insects. There are literally more than 1 million species of insects that are present. They all have a complex compound eye.
The first insects evolved around 400 million years ago. While they share a common ancestor with trilobites, they are not their direct descendants. Studies show they evolved their compound eyes independently, but from the same genetic blueprint: an array of microscopic lenses that work together to form an image. The greater the number, the finer the detail. Fruit flies have hundreds of lenses per eye. Bees boast an astonishing 7,000 lenses. But evolution drove one insect to develop a compound eye of staggering complexity: the dragonfly. Each eye has a mind-boggling 29,000 lenses, making for the ultimate motion detector. In pursuit of fast-moving prey, dragonflies give chase at a staggering 38 miles per hour. Their eyes' focusing power is poor, but their processing speed is spectacular, resolving images 5 times faster than our own. The result? Lightning reflexes, ideal for timing strikes and avoiding high-speed collisions. The success of insects has made the compound eye the most prevalent in all of nature. But it would not be the only vision system to emerge from the Cambrian explosion. Another group of animals evolved, one that would launch the prototype for an advanced eye of their own: the vertebrates.
The eyes of insects and the eyes of vertebrates represent different instances of the origin of eyes. They've evolved from different ancestors to achieve the same end.
The vertebrate eye gets its start as a simple light detector. Over time, it will evolve and become the targeting system for history's largest predators. When we look at Earth's creatures, we find that many of them look back with an eye akin to our own. In fact, one type of eye powers the vision of all vertebrates, animals with a backbone. A single-lensed camera made of soft tissue, known as the vertebrate eye. The vertebrate line includes reptiles, mammals, and birds. And they all have a common ancestor: a primitive worm-like animal that lived during the time of the Cambrian explosion. How this creature's crude eyes developed into the intricate organs we see with today has fascinated scientists since Darwin.
The vertebrate eye is really an icon of evolution. Early detractors of Darwin used it as an example of a feature that is so unbelievably complicated, and it's so obviously a machine, and there's so obviously the mark of an intelligent designer there. Darwin's famous response was to go through a series of intermediate evolutionary steps and show how you could start with a cluster of photosensitive cells on the surface of the skin. From there, you could create a pit eye, which essentially putting those photosensitive cells at the bottom of a pit creates the first directional sensitivity. And from there, you could evolve other sorts of focusing or accommodating parts of the eye, and essentially show that it was plausible that you could have a whole series of steps that lead up to a complex camera eye.
This new eye would sweep through the ocean, providing an advanced weapon in the escalating battle between predators and their prey. The genes for building the eye were passed down to all the branches of the vertebrate tree, from the first fish to sharks, and on to shallow water swimmers who would boldly set their sights on an unexploited world. Land, a new arena that one group of predators would come to dominate. These creatures, carnivorous dinosaurs, first evolved 230 million years ago. For the next 160 million years, they would rule the animal kingdom, littering the fossil record with the bones of their vanquished prey. What was it that made carnivorous dinosaurs such successful predators? Was it their size, their speed, their array of vicious weapons? Such traits are the stuff of any mega-predator, but they're useless without another key skill: the ability to target prey. Carnivorous dinosaurs surely possess some of the largest eyes in history. But how might their vision have helped them become such extraordinary predators? Paleontologist Kent Stevens made it his mission to find out.
Very interesting to know what it was like to be a dinosaur. What kind of vision did it have? How did it use its eyes?
Stevens faced a major obstacle. Unlike their bones, the eyes of dinosaurs have not stood the test of time.
It's essential to fill in the missing pieces because the soft tissue of the eyeball, of course, never is preserved. What you mostly have is just the bone.
Stevens used the bones to make scale models of dinosaur heads. These models would serve as a window into dinosaur vision.
What I came up with is a way to estimate how well the dinosaur could look out into the world by my looking at the animal.
Stevens devised a novel way to make his dinosaurs see. Lasers. The beam lit up the eye, allowing Stevens to plot its line of sight. When the illuminated eye became obscured by the creature's brow or snout, Stevens had reached the limit of what that eye could see.
I decided I will trace those lines of sight on an intervening glass between me and the animal, where if I couldn't see it, it couldn't see me.
By mapping the lines of sight of both eyes, Stevens could calculate their degree of overlap.
When I have these dots now, if I connect them, this actually represents the region which both eyes could see.
The area where Stevens's markings overlap is known as the binocular field of vision. What advantage does binocular vision provide?
Binocular vision, seeing something with two eyes, is very good for making fine depth judgments. If you have two eyes and you can simultaneously focus on an object in space in front of you, your brain can do a little bit of trig and decide exactly how far away that object is.
How would this aid a predator? Imagine a large dinosaur whose two eyes face to the side, resulting in two fields of view that don't overlap. This makes it difficult for the creature to see an object as distinct from its background and to gauge the distance to it. But if its eyes face more forward, their fields overlap, providing a degree of binocular vision. Suddenly, it's a 3D world. Engaging distance to a target is no longer a problem. Stevens knew if he could work out the binocular vision of carnivorous dinosaurs, he could determine how they hunted their prey. He trained his sights on the most iconic member of their group, Tyrannosaurus rex. With 13-inch canines, this 6-ton beast was certainly armed to the teeth. But did T-Rex have the targeting system to back up its bite?
T-Rex had 55 degrees, which is very substantial binocular overlap, as much as hawks.
Stevens concluded that this vision system allowed T-Rex to target its prey at a distance and pursue it on the run.
That certainly would have selective advantage toward being a better predator. You can just stay locked onto your target, and the amount of overlap could allow you to see how the world is moving as you're moving forward.
3D vision was a vital part of T-Rex's arsenal. And looking at skulls from different points in the animal's history, Stevens found it evolved even better 3D vision over time. Its snout narrowed and its cheeks hollowed out to allow for increasingly forward-facing eyes.
These animals reshaped their heads evolutionarily for a purpose. You see this steady progression toward more and more binocular vision, so it must have been of advantage to the animal.
With forward-facing 4-inch diameter eyes, T-Rex's vision likely ranked among the most detailed in the animal kingdom. But as Stevens discovered, not all carnivorous dinosaurs could hope to follow T-Rex's lead.
This is Allosaurus. He was the top predator in the late Jurassic. This animal has very lateral-facing eyes. And not only that, but there's a whole structure here along the top of the snout of this animal, which completely obliterates the view from the left eye to the animal's right and vice versa. So this animal has essentially blinders on it that keep it from being able to have a very wide field of view. Allosaurus turns out to have about 20 degrees of binocular overlap.
How could a dinosaur saddled with blinders be a top dog of the Jurassic? It turns out less binocular vision led Allosaurus to assume a craftier mode of predation.
Modern predators that have so little overlap between the two eyes, you tend to find that they are ambush predators, like a modern crocodile. One of the important aspects of an ambush predator is to be able to have surveillance and awareness of what's going on around it. So the idea of lateral-facing eyes is completely consistent with an ambush predator. They basically wait until the meal comes to them. They have a task of judging whether the time is right to lunge and try to take out the prey.
Dinosaurs show how the same winning strategy evolves again and again in predator vision. The opposite strategy holds true for prey animals. Their vision has evolved to help them escape their killers. As predators evolved eyes closer and closer together for targeting, the eyes of their prey moved further and further apart. Today, rabbits take this strategy to the extreme. 360-degree vision. Rabbit eyes evolved to sit high into the sides of its skull. While its vision is not three-dimensional, it allows the rabbit to see any threat at any angle. Rabbits, like humans, are mammals. And back when dinosaurs still ruled the Earth, our mammal ancestors had to do much more than keep an eye out. To survive, they had to find a new niche in vision, one that would allow them to coexist with creatures threatening their existence. 100 million years ago, dinosaurs rule the Earth. The odds are stacked against any animal competing with these mega predators, especially for the evolutionary newcomers, the world's first mammals, pint-sized animals not much larger than mice.
When the dinosaurs were running around, there were also mammals. But the only mammals that were around were very small, they'd fit in the palm of your hand, and they were just trying to keep out of the way of the dinosaurs.
For mammals, the era's underdogs, it was either scurry or be squashed. These tiny creatures adapted to an unexploited niche, the nighttime, and evolved a vision system that could thrive in the dark. Night vision, a triumph of eye evolution and a trait essential for survival in many mammal species today.
Many varieties of modern mammals also see well in the dark, and many of them are also nocturnal. And in some cases, at least, this is probably left over from their evolutionary heritage as small mammals hiding in the shadows of dinosaurs, emerging at night, and feeding.
What changes did evolution make to the eyes of nocturnal animals? That's a question Chris Kirk is trying to answer.
I tell my friends it's one of those things that you would have expected that somebody back in the 18th century went around collecting eyeballs. But to my surprise, when I started looking for data on just the gross anatomy of the eye, there was very little that had been published. And so spent, about a year and a half collecting eyes.
Kirk uses his extensive collection of eyeballs to study the mechanics of night vision. By putting his subjects eyeball to eyeball, he's able to compare them and see how their anatomy has evolved to deal with the dark. What's the difference between the eye of a day-active monkey called a marmoset and a night-active fat-tailed dwarf lemur? It's the size of their corneas.
The cornea is the window to your eye. It sets the ultimate limit on how much light your eye can gather.
The cornea is a clear curved shell that provides focusing power and ushers light into the pupil. The light hits the retina, where it is converted into electrical impulses that are funneled through the optic nerve to the brain. A complex process in the blink of an eye.
The diurnal monkey has got a very small cornea because it doesn't need to let in as much light, which you can see here, as the nocturnal lemur, which has a very large cornea that takes up nearly the entire anterior surface of the eyeball.
For night hunters, a bigger cornea is key to catching fast-moving critters in the dark. And one night hunter has pushed this anatomy to the max.
Tarsiers are something completely unique. There's nothing else like this in the world of vertebrate eyes. The diameter of the tarsier cornea is almost equal to the diameter of the eyeball.
There are 5,400 species of mammals. Relative to size, none have eyes as large as the tarsier. At 6 inches tall, it's one of the world's smallest predators. But its surveillance system outsizes the competition's.
So tarsiers need both highly sensitive vision and acute vision. One of the only ways you can get this is to build a bigger and bigger eye, and that's exactly what tarsiers have done.
How big? Try bigger than its own brain.
So this is the eye of a Philippine tarsier, and you can see that its cornea is actually a little bit larger than my own corneas. But what's really amazing about this is the fact that a tarsier's head is only this big.
The tarsier's eyes are so large, they need extra support to keep from tumbling out.
The eyeball extends past the margins of the orbit, and they have to have strong connective tissue in their eyelid to hold the eyeball in place.
With immobile eyes, the creature compensates with a neck that rotates more than 180 degrees. Tarsier's visual adaptations show the extremes to which evolution will go. Many mammals, such as big cats, evolved another way to boost their nocturnal vision. A staple in fables and fairy tales, glowing eyes have haunted children for centuries. A nightmare to some is evolution's gift to others.
And they can see us just fine. They can see us a lot better than we can see them, for sure. If one of them was over there stalking us, we wouldn't even know that they were there. Even, without this kind of light, they know when we're coming and they know who's coming.
Eyeshine functions as more than a mere scare tactic. It's an adaptation that has made cats spectacularly successful night hunters.
These guys, they're very active at night, and in fact, you can hear them making their noises, particularly the lion when he starts to roar, even at this hour, high-kiki. Also, the eyeshine, not only can they see their prey better, but also I think it makes them more intimidating to any other predators that are out there.
The source of the eyeshine is buried deep in the anatomy of the cat's eye.
Hold on to your hat.
Kirk's careful dissection reveals its inner workings. First, the retina. Then, the light-sensitive tissue lining the back of the eye. This area is known as the tapetum lucidum.
Tapetum lucidum is Latin for bright carpet. So it's the bright carpet in the back of your eye behind your retina.
So how does the tapetum work?
In your eye, or my eye, there's a black pigment behind the retina that absorbs the light so that it's not scattered. But in species with tapeta, any light that's not absorbed by the retina bounces off the tapetum, the mirror behind the retina, and essentially has a second chance to be absorbed. So you've got twice the chance to absorb every incoming photon of light that your eye captures.
On the rebound, some of the light shoots back out of the eye, resulting in a glowing effect. For cats, this mechanism yields extraordinary benefits. They require only 1/6 of the light that humans need to be active in the dark.
I think of the tapetum as just this marvelous adaptation. It's such an elegant solution to a pretty straightforward biological problem. And, putting a mirror behind your retina to increase sensitivity, what could be simpler?
Cats were far from the only mammal group to evolve such an ingenious solution to night vision. Other species would reach the same result entirely on their own.
But I think really the most interesting thing about the evolution of the tapetum lucidum is that it's such a good solution to this problem of enhancing sensitivity that many, many different groups of mammals have arrived at this same solution independently.
What about us? Even though we are mammals, we struggle to see clearly at night. That's because 30 million years ago, our ancestors shifted from the night to the day. When these monkey-like creatures moved to a new niche, they would evolve eyes that could see the world like never before. The human eye, able to decipher 2.3 million colors with speed and precision that makes a computer look slow. Our color vision is superior to that of many other mammals, who must get by with far less. To a dog, the world is virtually devoid of color. Only a small number of species, including our primate relatives, can see a full range of yellows, blues, greens, and most significantly, reds. But such adept color vision does not exist in the earliest primates. Its evolution has its roots in the aftermath of a mass extinction.
About 66 million years ago, a gigantic asteroid caused the extinction of all non-avian dinosaurs and paved the way for the rise of mammals.
After the dinosaurs disappear, mammals radiate. All of a sudden, they start diversifying, and one group of mammals is the primates, and they go straight for the trees.
Once primates settle into the forest canopy, they evolve into new species. One of those lineages becomes day active, the ancestors of today's monkeys, apes, and humans. They evolve a new adaptation in their eyes not seen in earlier species, an expansion of their color vision. A standard range of colors consisting of blues and greens now include red. Why would primates need to see red in their new world? For clues, biologists look to primates today.
Howling monkeys are this wonderful, unique animal that may give us some insights into our own evolutionary past.
Biologist Nate Dominy has spent his career researching primates as a means of understanding our own evolution.
They're almost like a time machine for looking at what the ancestral monkey in Africa and Asia might have been like. We might get clues to what its diet was like, its social behavior, its anatomy, and that ancestral animal was the one that gave rise to all subsequent monkeys and apes and ultimately humans.
Dominy wanted to know why natural selection favored improved color vision in our ancestors. What did they gain by evolving to see the color red? Dominy went on a year-long journey to study primates in their natural habitats.
Part of my PhD research was to go to Africa to study monkeys with different diets and to study chimpanzees and to see if there was some sort of common or unifying food item that they might have all turned to that might explain why these monkeys all routinely share a very similar type of color vision.
Dominy scanned the rainforest canopy for test subjects, hoping to capture leaf samples from where the monkeys had stopped to eat. But he had a problem. What a monkey eats was high above his reach.
It's challenging in the rainforest in particular. When an animal is at the top of that tree eating something and you want the sample, there's not many ways to get it.
Left with no other choice, he had to take up arms.
We use this very stout, handmade slingshot from Panama that fire small pebbles up into the canopy and leaves will come down. And it's a great way for sampling the types of foods that primates might eat.
After collecting and packing up the key samples, Dominy's real work began. Using an instrument called a spectrometer, he recorded the color of each leaf he had gathered in the field.
You see that peak in this green spectrum? So that's telling you that this is a green leaf. Now you see how, compared to that last one, This is peaking much more here in this orange region into the red region.
Nate's data yielded a remarkable discovery. Not only were the monkeys eating red leaves composed the majority of their diet. It turns out the redder the leaf, the younger and more nutritious it is.
Old, mature leaves, they're green leaves, they are tough, they're full of toxins. They're generally leaves you want to avoid. So primates in general tend to go for the youngest leaves possible. And if those young leaves also have a color cue that distinguishes them from mature leaves, then it may be advantageous to evolve a mechanism for detecting those young leaves.
To primates, red wasn't simply another color. It was a beacon, a homing device, allowing them to target their key food source from a distance.
If it sees red leaves in the canopy, then it knows automatically that those particular leaves are young. And so it can save energy, it can save time, it can travel directly to those young red leaves rather than randomly searching throughout its environment.
Increased color vision, a strategic evolutionary leap that scientists discovered was one of many. Primates would soon reap the rewards of another crucial adaptation, binocular vision. It's a trait that predators have repeatedly evolved. But for primates, it served a new function.
Primates have eyes at the front of their head, but they're not predators, so why would they do that? Great thing about having two eyes pointing the same direction is you get depth perception. If you're going to jump from one tree and try to land on another tree, depth perception is a really good trick to have.
Over time, primates evolved a binocular field of vision of 60 degrees, on par with birds of prey. It's an evolutionary step that allows primates to capitalize on their hand-eye coordination. But this increased binocular vision comes at a price. Unlike the rabbit, primates now had a limited field of view.
Most animals have eyes that are laterally placed on their heads, which is to say the eyes are on the side of the heads. And this provides these animals with a panoramic view. And that's really, really useful for detecting predators that may be coming from behind you. So there's a significant cost to putting your eyes in the front of your head. But the advantages are that you have better depth perception, you have better acuity.
Once primates abandoned a vision system built for protection, birds of prey were ready to benefit. Swooping in from the sky and plucking primates from the treetops, these aerial terrors were threats to be reckoned with.
Based upon the evidence that we have from the fossils, birds of prey have been exerting some type of selective pressure on primates for as long as there have been primates and raptors.
Primates were easy targets for these winged predators. Under siege, primates evolved a new kind of behavior. They had to depend on each other.
You can imagine then that once these animals evolved eyes on the front of their heads, they needed to live with other animals so that they could improve the probability of detecting a potential predator.
Group living was the primates' answer to predation. It allowed them to maintain their high degree of binocular field of vision without sacrificing safety. Their keeping watch with a communal eye resulted in an evolutionary side effect: larger, more powerful brains.
So you can see the evolution of group living. And once group living evolves, you have a strong selective pressure, or you might say that evolution favored larger brains, because that's more individuals that you have to remember.
Fossils show how the visual system of primates improved over time. Both the eye sockets and the optic nerve canal grew larger as brain size increased. Primates put huge demands on their sight, from color vision to increased binocular vision. They became extremely sensitive to the slightest change of expression on the faces of other primates. This increased need for visual processing fueled the development of intelligence.
And you can see how this sort of runaway process for group living, larger brains, avoiding predation, could give you the suite of characteristics that define the primate order to which we belong.
A complex and mysterious organ, one that has fueled evolution for more than 500 million years, driving an eternal arms race between predator and prey, and becoming an indispensable tool for millions of species. The eye, an engine of evolution and one of its ultimate masterpieces.